The next thing we have to deal with is convection. Convection is energy transfer between a solid surface and an adjacent gas or liquid. Okay, that's what's happening with convection. So convection has two components. It's going to have that conduction, that diffusion of energy. Just like, there's nothing that's changing because we have that solid and we have a liquid there. There's still going to be that diffusion of energy from a hotter surface to a colder medium. There's still going to be that's happening. But what else is going to happen is going to be the advection, or the bulk movement of energy away from the surface. Okay, the difference between conduction and convection. In a convection, that gas or that liquid can move. The solid, it can't. It's just sitting there. So that's why diffusion is the only thing it can do. But what's happening in a liquid and a gas is it's now flowing. It can now take that diffusion of energy and then make it flow away. And so that's where we get the word convection, convection. Two things happening there. Okay. Now, any surface that's in contact with a gas, any surface that's in contact with a liquid is going to have convection. Right now, my head is convecting right now, and that makes point. There's two types of convection. Two types. The first one is free convection. Okay. Here, buoyancy forces dominate. Okay, buoyancy forces dominate. So my head, I'm alive, so I have my temperature here is about 98.6 or something like that, and I am going to be. The environment around me is 78 degrees, so I'm going to have heat transfer from my head to the air around it. And what's going to happen is my head is going to add heat to that air. That air is going to change its density. It's going to become more buoyant because it's going to be lighter. And that air particle is going to then move upward because of the heat has changed its density, moving away. And so I'm going to have this plume of heat moving off of my hair. If you had something called Schlieren photography, I encourage you to look up on YouTube Schlieren photography, Schlieren photography. You could see the plume of heat moving away from it naturally because of the buoyancy forces that are created. Now there's another type of convection, and that is forced convection. And this is you're going to have an external mechanism. Okay, here's my external mechanism. I'll turn it on right here. I got a fan in the room. All right, there I go. You can't see it. Here we go. Let's go up here. Look at that. There's my external mechanism. There's a fan. Not changing the temperature of the room at all. We're not doing anything to the temperature of the room, but man, all of a sudden I feel cooler. Why? Because now I have this movement. Now it's not just naturally moving the heat off of my hair. Now it's moving it faster. It's blowing that warm air, that I've warmed up through conduction, that diffusion. It's moving it away faster, and man, I feel cooler. I haven't done anything to the temperature of the room. The room's still 78 degrees, but that movement of air is making me feel cooler. Okay, so how do we define or how do we analyze this? It's something called Newton's law of cooling. Okay, Newton did almost everything. All his F equals ma, everything that we know about Newton. He did it before he was like 30, I don't know, 35. I forget exactly. I was reading something. He did most of it in a pandemic. It's kind of interesting time to do it. And then what he did was he spent the rest of his life trying to turn substances into gold. He made all these wonderful contributions. We know him so well. And then he spent the bulk part of his life doing something that was a little silly, but to each their own. He added in, he changed our lives in many different ways. Okay, so Newton's law of cooling is this. Q dot convection is going to be equal to HA times TB minus TF. And I'll tell you what these things mean here in a second. So H is going to be the heat transfer coefficient. And this is going to be in watts per meter squared Kelvin, or it's going to be in BTUs per hour per inch squared per degree Rankine. Okay, that's the heat transfer coefficient. Area is going to be the surface area. TB is equal to the temperature of the surface. Or sometimes I call this the base. And TF is the temperature of the fluid. Okay, fluid, liquids, and gases are fluids. Now, sometimes your book will call this temperature of the surface, TS, temperature of the surroundings, TSUR. Well, surface and surroundings both start with the same three letters, so I like to say base and fluid. Okay, whatever makes you happy. I don't care how you work on it. It's another way of writing this is Q dot is equal to HA times delta T. Okay. Now, note this. This is very important, and it's something that you have to think about. What we're going to want to do with these temperatures here is these can be changed. You can do fluid minus base. You could do base minus fluid. We put the high temperature first. Okay, we put the high temperature first because we don't know. When we're making this analysis, we don't know which direction the heat's moving just by using the equation. We don't know if the base is always hotter than the fluid or the fluid's always hotter than the base. So you're going to have to make that decision when you write this equation. And what it's going to show us is when we put the hot one forward, that's going to be the heat transfer, and then we can go and look at it logically and make the direction, the thermodynamic sign convention that goes into our first law. Okay, if the base is our system, or if our system is the solid, then we can say, hey, it's coming out of our solid, so it's going to be negative. If the base is colder, it's coming into. It's going to be, if it's coming out of, it's going to be negative. It's coming into, it's going to be positive. I flipped a couple things today. I want to make sure that we got that correct. When you're looking at that sign convention, going into a substance is going to be positive, going out of a substance is going to be negative. So we have to consider how we're looking at this. So for example, let me just draw this, and I'm saying this is my system. This is a gas, and it has a solid around it. And I'm blowing air over the top of this, air over the top of this situation. And I find here that this here is 100 degrees Celsius, and the air here is 20 degrees Celsius. Well, I'm going to put in here HA times 100 minus 20, and I'm going to know this is going to give me some positive number. And what I know then is this is going to be heat leaving this system. Heat's leaving the system, and I guess my marker is going to have to catch up there a little bit. Okay, heat's leaving the system. Now, if my thermodynamic system is going to be this this dotted line, when I write my law here, my delta E is equal to Q minus W, or in this case actually, dE dt is equal to Q dot minus W dot. Now what I'm going to put in here for my Q dot is going to be a negative this calculation here, because that is opposite. It's opposite of what it's going out of my system, so it's going to be negative for this law. So even though I calculated it as a positive number, I had to make a decision about how I put it into this first law equation, and this is going to be a negative putting into this first law equation, okay, because it's leaving my system. Okay, that being said, it doesn't matter if your delta T in this case is relative or absolute. It doesn't matter if it's degrees Celsius or degree Kelvin. It doesn't matter. Same thing as degree Fahrenheit. It doesn't matter if it's degree Fahrenheit or degree Rankine. It doesn't matter. It just does not matter. You can do either of those. But if you're worried about it, always convert to absolute, and you'll never mess up. Okay. Here's one thing that you need to know about this. This H, this heat transfer coefficient. This is not a property. It's not a property. In fact, when you take heat transfer, you will spend a lot of time trying to figure out what this H is. H is dependent upon the situation. Is the fan blowing a little bit? Is the fan really blowing on it? Is the flow over the surface laminar? Is the flow blowing over the surface turbulent? Is my surface rough? Is my surface smooth? All these things are going to change my heat transfer coefficient. So this is not something you can look up. It's not a property. It's not something you can look up in the back of the book. You're going to have to calculate this. And the calculation of this is very challenging. In fact, we have done computer models and everything, and we have not been able to really get these numbers down really well. For example, if we get a heat transfer coefficient that's within 10 or 20% of the actual value, so maybe we do an experiment, we measure the heat transfer, and we say, oh, the heat transfer is 20. Okay, now we want to model that, and so we model an equation, and we try to calculate what the heat transfer coefficient is. If we get within 20% of that experimental value, we are overjoyed, and we're like, that's a great numerical estimation of our value. Now, 20%. Can you imagine if I was within 20% of your grade? If you got an 80 in your class and you could get anywhere between 100% or a 60, and I was like, oh, that's great, I'm within 20% of what you actually got. No, you would be livid. But in this, in heat transfer, we are really good if we are within 20% of our final answer. Okay, so let's look at some typical heat transfer coefficients. Okay, for free convection, in gases and in liquids, here's our H, and this is going to be in watts per meter squared Kelvin. Gases, we can go between 2 and 25. Liquids, it's between 50 and 1,000. So of course, for free convection, if you had a steak you wanted to thaw, it was frozen, and you leave it out on the counter in a gas, it's not going to have as much heat transfer as if you put it into a liquid. And that's just because the molecules are closer together in the liquid, they can diffuse that heat away from it faster. Okay, in forced convection, we're going to have gases that are going to be between 25 and 250, and liquids that are between 50 and 20,000. Okay, so we want to do what we can to get ourselves into a liquid state or gaseous state and make sure that we're either forced or free, depending on what's going on, to write this equation. Q dot is equal to HA times delta T. Now, you may see some things. Convection, these things are in your computer. These are heat sinks. These things are in your computer. What happens here, you see on this heat sink, there is some thermal paste here, connecting it to a CPU. Here I have a processor here, old processor. Okay, it's connected to here, and I want to dissipate heat from something, and so I'm gonna put, first of all, I'm gonna put thermal paste on the bottom of this heat sink, and that's gonna connect it to that chip, that processor really well, and have really good conduction from that chip into this heat sink. And now what I want to do is I want to make this heat sink, I'm putting fins on it. Why do I put fins on this heat sink? If you look at that equation I have there, the fins are going to make the surface area go up. The more surface area I have, the more convection I can have. And then I'm going to blow air through this, blow air over this, so that I can remove the heat, and there's going to be a different heat transfer coefficient. So you're going to see a lot of heat sinks like this. The radiator in your car works by convection. There's hot fluids coming through there. It's probably, maybe it's coolant, maybe it's oils, depending on what kind of radiator you're having there. There's air flowing through it. This air is flowing through it, taking heat out of that system by a series of fins. What's interesting, it's called a radiator, but it's actually primary mode of heat transfer is actually convection. So that's an interesting thing. It's an interesting thing right there. So convection is something that we deal with all the time. We need to understand that our equation is very simple, but we need to understand how do we deal with convection.